I'm going to talk a little bit about the Lro Extended Mission and some recent highlights. And I know there's little time, so I'll move quickly. We are in our extended mission from what started off as an Exploration System Mission Directorate mission, measurement mission in 2009. Here's a list of the instruments that we carry on board. We have 7 instruments, including the laser altimeter, the wide-angle camera, or the camera suite, the wide-angle camera, the narrow-angle cameras, the diviner instruments, a radar, cosmic ray instrument, the lens neutron detector, as well as the lamp instrument, which is the UV spectrograph, imaging spectrograph. Because we have follow-on talks by the diviner team and the LROC team, I thought I would confine my highlights to, for the most part, to the other instruments in the interest of time. But if you want a more detailed overview of what LRO is doing, I wanted to bring everyone's attention to the recent AGU volume that was published, mostly of JGR papers, but also other journals, AGU journals. A total of 44 manuscripts, mostly by the LRO team, but also other folks who used LRO data and published in JGR. So here are some of the key dates. Again, we launched in June of 2009, and now we are currently in our extended mission and are scheduled to complete the mission next year in September. I wanted to say something about the orbits that we're in currently. So we started the mission off in a commissioning orbit. That orbit is something that very low cost to maintain. Once we commissioned the instruments and the spacecraft, we went down into a average 50-kilometer circular orbit, and we stayed in there for a considerable amount of time, but it is an expensive orbit to maintain, and so we ended up essentially back into the commissioning orbit, and that's where we are right now. So we have on board the spacecraft around 40 kilograms of propellant, but that is sufficient propellant that we could last conservatively as long as 6 more years. So in this extended mission, I wanted to just quickly go over the major themes of the mission. We're interested in polar volatiles on the moon, especially polar volatiles, solar system, early history and planetary processes, the impact record, and the moon's interaction with the external environment. And as I said, I'm really going to concentrate on some of the instruments that tend to emphasize the first and the last topic, knowing that Divine and LROC will talk some more about some of the other topics. Dave just gave us a very nice presentation on the Grail mission, and he talked at the end about the end of the mission, and that's where LRO participated in. We had an opportunity to look at the impact while it was happening, and then also subsequent to that. And this is from an animation that shows the 2 Grail spacecraft location just before the impact and where LRO was. So we phased the LRO orbit so that we would be at closest approach. So it was an opportunity very similar to the L-Cross impact, but the major differences are that the Grail spacecraft were much lighter, moving at much lower velocity, and we were a considerable distance away. We did have one advantage in this measurement, and this is from later on in the animation showing the instrument lamp slit, observation slit, as we passed over the Grail impact site. And what you'll see from this is that the slit has, part of it is on the moon itself. Now that's not where the impact is. The impact was in front of this, and it was necessary for the plume to rise into the sunlight for it to be detected. But with having the slit on the moon, you have a very dark background, and that wasn't the case with the L-cross impact. And that presented the LAMP team the ability to observe in this impact hydrogen atoms evolving from the impact, whereas it may have occurred in L-cross as well, but because of the background, couldn't be discerned. They also saw in this Mercury. So, it was a much fainter signal than L-cross, but there were some good science observations made. And then subsequent to that, David already mentioned, but here's the images from the narrow-angle camera, the LROC instruments, and I don't know, probably can't make it out in this, but between the two, vertically you have Grail A and Grail B. You can actually see the impact site. So LAMP, as I said, saw hydrogen atoms from the Grail impact. From L-cross, they saw H2, and also as part of their measurements, they've seen a significant amount of H2, and this is in reference to the Cook paper on upper limits for around 30 species that Jasper just talked about. And so this is the picture from the paper that they published, and what you see here is that they have a clear signature of the hydrogen. They have clear signatures of the helium, but the great mystery here is where is the argon? And if you look at the lower left there, where we're showing the geometry, and as Jasper pointed out, for this measurement, we're primarily looking on the dark side. So LRO is looking down onto the dark background of the dark side through the illuminated exosphere. And it's possible that maybe that the argon does exist there, but on the moon, certainly it was observed during Apollo, and the reason we're not seeing it, as Jasper alluded to, is the way we're making that measurement here. And so as we go forward, we're going to try to improve the geometry and the way we do this in order to look at other near terminator locations, hopefully on the day side as well. And again, on the left here is the sort of the LAMP slit over the L-cross impact, and I talk about the H2 that was observed, and that was actually kind of a surprise, and it gives me an opportunity to talk about how LRO is as a mature mission, is now investigating questions that have been made early in the mission. And so the Crater team, which is the radiation cosmic ray detector, has looked into the H2 that was observed and suggests that the H2 is actually being formed as a result of radiation chemistry. And so, H2, even in these permanently shadowed regions, are not thermally stable. But if the H2 is created in the regolith itself, tens of centimeters beneath it, the residence time may still be geologically very long, and could possibly explain the presence of the H2 that we observe. And then moving on to some of the other crater observations, there's a recent publication on the efficiency of plastic material. So Crater does carry a tissue equivalent plastic in its telescope, and so it has these two blocks of plastic, and through just observing the energy deposited into the exterior detectors and the interior detectors, they're able to measure very precisely the energy that's deposited into the plastic. And the main purpose originally is for the understanding of the potential biological impacts, but they've shown that plastic will work as an extremely good shield, more efficient than aluminum as a function of mass. The other radiation detector is that we have on board is the neutron detector, and I just wanted to show one of the more recent maps of the neutron a deficit measurement, which is related to hydrogen over the South Pole, and I urge you to look at some follow-on posters given by the LEN team, which kind of discusses our understanding of the distribution of hydrogen in the permanently shadowed areas, and the fact that what they're seeing is that not all the hydrogen is sequestered in these PSRs. And so they're looking at topographic correlations, and they're seeing as well some diurnal effects, not over the poles, but at lower latitudes. The mini RF instrument, the transmitter on that has failed, but what the mini RF team is doing is some very innovative measurements for bistatic measurements of radar reflections. And so the idea here is associated with the potential of discriminating ice from rocky subsurface. The radar return, the circular polarization ratio for both rocky and for ice deposits lead to an increased circular polarization ratio. And their idea for distinguishing the two is that the fact that the rock, which is the result of multiple reflections of surfaces equal or larger than the wavelengths, would have a slow fall off in CPR as a function of the beta angle, whereas the ice, which is primarily a coherent backscattering effect, would have a sharper drop off. And so they're looking very closely, and the example here is for a Kepler Crater, which is really a calibration work that they're doing, and also they're getting some science on the regolith in that area. And this is just showing that they can do views of the South Pole from Arecibo. Another LOLA publication that has just come out that I wanted to show you was the recent measurements of the surface roughness of the moon at different scale lengths. And so LOLA is doing some tremendous work filling in gaps for their topography, but now they're doing some more detailed studies. And so one of the things that comes out of this is that for different scale lengths, the distribution of the roughness is very different. Whether it's 100 meter or kilometer kinds of scale lengths. And that is one might have thought that it was more fractal and that it'd be invariant and over scale, but what they're seeing is that is not the case. And this is just a stretch of the same data. As a mission moving forward, we have opportunities for combined data sets, and so here is just a couple of examples. Again, LOLA reflections and mini RF. These are on the right for reflections over Shackleton Crater, giving upper limits for ice surface and deposited ice, and then Tsiolkovsky Crater using multiple data sets as well. upcoming opportunities, and Jasper already spoke about this, but we're really looking forward to the LADI mission. We just had a meeting with the LADI team and the Artemis team discussing what we could possibly do. The measurements from LRO, especially the helium measurements, along with the LADI measurements, we can give a latitude dependence versus the longitudinal dependence of LADI and really anchor the measurements to each other. I think it will have a really good benefit, and this is made possible by the fact that we will be in a opportune beta angle at the time of the measurement, assuming that the LADI doesn't get delayed from its current launch date. So we worked very hard to put all this data in the planetary data system. It's a very rich data set. We encourage everyone to use that as much as possible. I see that I'm out of time. So I'll just quickly move to the end. We worked very hard to with the public engagement and telling the LRO story to the public. Thank you.
Thanks very much, John. Just great. I think that I speak on behalf of the entire lunar science community when I say that we all owe you and your team at Goddard, and then of course all of the PIs all over the world, a huge, huge debt of gratitude for all the incredible data that you've returned to us. So thank you for your talk, and thank you for that. Before I take any questions here, I want to remind people that you can ask questions over the hub, as I mentioned a couple of hours ago. Just say in chat that you would like to do that. I also want to say that all of the earlier talks are already online. So for people that have just joined us, you can during the break you can take a look and see some of the talks that you might have missed. So let's see. There's a question from Valbir Singh at the Manipal Institute of Technology, which I'm not sure I quite understand this, but I believe he's asking why LROs in a polar orbit. If you want to just go ahead and answer it, I think I probably could as well, but go ahead.
Well, LRO is a polar mission, definitely, and with the moon rotating underneath us, we're able to get the whole moon, and also we were formulated to look at the resources that may be sequestered over the poles. So that was the reason. The LADI mission is equatorial, and that gives them many opportunities to go through the to get that latitude variation in a short mission.
Okay, great, thanks. Do you want to?
Sure.
Yeah, Jen Heldman has a question here, John.
Hey, John, I was just wondering if you could tell us about some of the specific species that you saw from LRO during the Grail impact, and if there are any interesting or unexpected conclusions regarding the composition of regolith at those sites.
I think the only two that the lab team has reported is for the Grail impact was mercury, which was also seen for L-Cross, and then hydrogen atoms. And and I think the lab team might say that the hydrogen is still a preliminary. The signal was very faint. But that is it. I think those are the only two definitive measurements.
Okay, great. Well, we're going to move on. John, thank you very much again for a great talk and for all your